Hello students, welcome to this session. Here we are going to discuss one more application of the flip-flops, and this is called as counter. A counter is a sequential circuit, so that will count the number of clock pulses that arrives at the clock input. That is called as a counter. So if the counter performs the counting operation in terms of binary, then it is called as the binary counter. So actually here we are using flip-flops, and these flip-flops will be interconnected in such a way that they are going to count the number of flip clock pulses that arrives at the clock input. So depending on how we are going to trigger these flip-flops, okay, which is called as a triggering pulse. So triggering pulse, here it is nothing but the clock signal that we give. There are two types of counters. They are asynchronous counter as well as the synchronous counter. First, we'll see what is the meaning of an asynchronous counter. So here in asynchronous counter, the flip-flops will be clocked sequentially. So the meaning of sequential clocking is that the output of one flip-flop will be fed as input to the next flip-flop, and that input it is given to the clock input. That is called as the synchronous counter. So in the synchronous counter, the output of the first flip-flop, it is fed to the clock input of the second flip-flop, and the output of the second flip-flop will be fed as input to the third flip-flop, and it is going to continue. So the succeeding flip-flops, they are going to be driven by the previous flip-flops. So here in this case, delay will be more. Now let us move on in order to see what is the meaning of a synchronous counter. In synchronous counter, we are using flip-flops, and these flip-flops will be clocked simultaneously. That means all the flip-flops will get the clock pulse at the same instant of time. So here, since we are clocking the flip-flops simultaneously, obviously the delay will be less. But as per the syllabus that we need to have to discuss only the asynchronous counters. So here these asynchronous counters, they are also known as the ripple counter. So now we are supposed to see the 3-bit binary ripple counter. So in order to see this 3-bit binary counter, ripple counter, first we have to see the construction of this. So 3-bit ripple counter, this is also known as modulo 8 counter, because it is with this we are going to get the 3 outputs, which are Q0, Q1 and Q2. So with 3 bits, we could get 8 different combinations from 0 to 7. That's why it is called as modulo 8 counter. And it is 3 bits that are used over here. Every bit we require one flip-flop. So in order to construct this one, we are using T flip-flops over here. Look at the construction of this. This is an asynchronous counter, which is constructed using the T flip-flop. So here is the first T flip-flop. Output of this is represented as Q0, and this Q0, it is fed to the clock input of the second flip-flop, and Q1 is the output of the second flip-flop, and that is fed as input to the clock input of the third flip-flop. So this kind of connection, it is called as the construction of the asynchronous counter. So clock is fed to the only to the first flip-flop, but it will not be given to the succeeding flip-flop from this clock, but it is going to be given by the previous flip-flop output. Okay, so that is the construction of the asynchronous counter. Okay, now let us see the working, how it is going to count 8 numbers over here. That is important. So counter, initially it is reset. So you all know that it is reset means all these flip-flops, they will have 0, 0, 0. So initially reset, it is Q2, Q1, Q0, there are zeros over here. So when the first clock pulse is applied, so when the first clock pulse is applied over to the first flip-flop, so flip-flop, this flip-flop we are taking it as flip-flop 0. So this flip-flop is going to toggle because here T flip-flop we have used. So this flip-flop will toggle at the negative edge. So thereby the output of the first flip-flop, that is F flip-flop 0, it goes from 0 to 1. Okay, so this input, it is applied during the negative edge of flip-flop 1. So the output of flip-flop 1, it is not going to change. Okay, so this input, so what is this input? We are going to get 1 over here. This will be applied during the negative edge of flip-flop 1. Okay, so negative edge of the clock to the flip-flop 1. So because of that, it is not, the output of flip-flop 1 is not going to change. So thereby we are getting Q2, Q1, Q0 as 0, 0, 0. So when the second clock pulse is applied, so at the negative edge of the second clock pulse, so flip-flop 0 is going to toggle. So when it toggles, Q0 changes from 1 to 0. So at this negative edge that is applied to the clock flip-flop 1, so thereby the output of Q1 toggles. So Q1, it changes from 0 to 1. So this is, it is going to continue. So here what happens? So this will be the input to the last flip-flop. So because of this positive edge that is coming over here for the clock, it will not change. So thereby only 2 flip-flops are going to change their state. So thereby Q2 is 0. So thereby we'll get the output as Q2, Q1, Q0 is equal to 0, 1, 0. So after the application of the first flip-flop, we could see that Q0 was 1. Now after the application of the second clock pulse, we could see that the output of the second flip-flop is 1. And after the application of succeeding flip-flop pulses, it is going to continue until we get 1, 1, 1 at the output. Okay, so this is the truth table. You already know how to write the binary table over here. Okay, so these are the number of clock pulses. So here I said it is clock pulse 1, 2 like that. So if you start the clock pulses from 0, so it is from 0 to 7. So it is totally 8 clock pulses that are applied, and we will get 8 different combinations over here that we are going to get. Okay, so this is the timing diagram over here. This timing diagram it is more clear that you can see over here. So at the first clock pulse, so at the negative edge of the first clock pulse, Q0, that is the first flip-flop, is going to toggle. So thereby it will toggle from 0, it goes to this particular state. Okay, so at this instant what happens? It is given to the second flip-flop, is it not? So it is given to the second flip-flop, so thereby the second flip-flop is going to change. So it is going to be set. Okay, so it is going to toggle. So thereby here it changes the state from 0 to 1, and it remains in the set state for 2 clock pulses, and then it is going to change the state. So after the application of every clock signal, it is toggling. The first flip-flop will continue to toggle, but the second one will toggle during only this time, and it is at this time. So obviously Q2 will toggle only once over here, because here it is at the 4th clock pulse. It is going to get the input. So it will toggle and it will continue to be in that same state. So with this, vertically you see, and you need to have to write this. How to write this one here? Start from Q0, Q1, Q2. So it is 0, 0, 0. So it is state 0 that we are writing. Here it is 0, 0, 1. So it is 1. 0, 1, 0. It is 2. 0, 1, 1, 3. 1, 0, 0, 4. 1, 0, 1, 5. So like this we need to have to write the rest of the things. So now we'll see how to convert this modulo 8 counter into modulo 5 ripple counter. The meaning of modulo 5 ripple counter is that it is going to count only 5 clock pulses, not more than that. So in order to count only 5 clock pulses, what we need to have to do? You could see that number 5, it is represented as 101. Okay, so this is the output of the third, that is Q2. This is the output of the third flip-flop, which is Q2, and this is the output of the first flip-flop, which is Q0. So wherever 1 is present, you are supposed to take the tappings from there. Here Q0 is 1 and Q2 is 1. You take the tapping from that particular flip-flop and feed that through a NAND gate. So when we feed it through the NAND gate, when both the inputs are 1, 1, obviously we are going to get 0 over here. So thereby that 0 will be applied to the clear input of this T flip-flops. Okay, so it is applied to the clear input of T flip-flops. So thereby we are going to get 0, 0, 0. Okay, so after the 5 clock pulses, we are taking the output from the first flip-flop as well as the last flip-flop, and it is fed through the NAND gate, and the output of NAND gate, it goes to clear input. Okay, so this here it is not been mentioned. So all these, they represent the clear input of the flip-flop. Okay, so if C is, it is 0 over here, then what happens? It is going to clear the flip-flop, right? So thereby it is going to count only the 5 clock pulses. So here is the truth table. So this truth table, how it counts is, so after the application of the first clock pulse, so all these are 0 zeros, and after the application of the clock pulse 1, so here it is 0, this is clock pulse 1. One of the flip-flops is going to toggle, that is Q0. We are going to get, this is flip-flop 0. So thereby the output is 0, 1, 0. So when we apply one more clock pulse, that time what happens? This will be coming over here at the Q1. So thereby we'll get the output as 0, 1, 0. So like this, when we get the output as 1, 0, 1, that means after 5, we need to have to go back to 0 state. In order to do that, how we need to have to change is, wherever we are getting 1, okay, here we'll get at flip-flop 0 output is 1, and flip-flop 2 is also 1. So take them and pass them through the NAND gate and give it to the clear input. So thereby, once the 5th clock pulse, that is once you get the count as 5, it resets. That means what? It will go back to 0 state. Okay, so here is the timing diagram for it. So timing diagram, it will resemble the modulo 8 timing diagram, but here we are representing only 5 clock pulses. That's all. We'll have only 5 clock pulses. That's all. Okay, now let us see the difference between the asynchronous and the synchronous counters. So asynchronous counters, flip-flops are connected in such a way that the output of one flip-flop is fed as the clock input of the next flip-flop. So it is serially, it is given. Okay, but in the synchronous counters, there is no connection between the output of first flip-flop and the clock of the second flip-flop, but they will be simultaneously clocked. Okay, so that we could see in the second difference. So here in the case of asynchronous counters, we'll have it is not clocked simultaneously, but synchronous counters, all the flip-flops will be clocked simultaneously. And with respect to the design, logic circuit is quite simple in asynchronous counters, but it is quite complex in synchronous counters. So we have one drawback here in asynchronous counters. Obviously, the propagation delay is more because output of one flip-flop is going to drive the next flip-flop. So thereby delay will be more. But there is no propagation delay with respect to synchronous counters because all the flip-flops are clocked simultaneously. Thank you, students.